Welcome to this explainer. Today, we're literally stepping into the shoes of a systems architect to dissect a truly critical evolution in software engineering, the 5 pillars that guarantee long-term system correctness for high-scale LLM infrastructure. Look, if you're out there building complex, automated systems, you already know that keeping them reliable at scale isn't just a goal, it's the ultimate challenge.
All right, here's our blueprint for today. We'll be looking at 1. Tokens to system correctness. 2. The Structural Fidelity Score foundation. 3. Guardrails for preserving intent and logic. 4. Upstream validation to catch contradictions. And finally, 5. Telemetry for long-term reliability. We're going to see exactly how to shift our infrastructure from mere cost savings to rock-solid systemic reliability.
Section 1. Tokens to system correctness. This is the big paradigm shift in production, taking us from a brittle prototype to a truly robust enterprise system.
So back in the early days of LLMs, which, let's be honest, feels like a century ago, optimizing prompts just to shave off a few tokens was the gold standard. The entire focus was on cutting costs. And hey, that was perfectly fine for simple demos, but there was a massive hidden danger. You were constantly risking dropping critical logic. Today, for complex, multi-step agentic workflows, reliability demands guaranteed structural correctness. We absolutely have to know that when we optimize a prompt, we aren't mutating its fundamental instructions.
There's a quote here that just brilliantly hits the nail on the head regarding our core thesis as engineers. The difference between a tool you can demo and one you can deploy is moving from token reduction to correctness guarantees. Day 1 correctness is just table stakes. Day 100 correctness, that's your deployment prerequisite. You simply cannot deploy an autonomous pipeline if you don't have hard guarantees that your underlying prompts are going to survive thousands of optimization cycles intact.
Moving right along to our foundation, the Structural Fidelity Score, which is Pillar 1. Because, as any systems architect knows, if you can't measure it, you have zero baseline for reliability. Enter the Structural Fidelity Score. We inject this automatically right after every single LLM and hybrid optimization call. What it does is provide a deterministic per-optimization signal that measures exactly how much an optimized prompt diverges structurally from your original input. Say your original prompt enforces a super strict JSON schema. Well, Pillar 1 mathematically verifies that the optimizer hasn't quietly dropped that JSON requirement. It gives you a quantifiable confidence signal, so you're not just crossing your fingers and hoping for the best. And to prove we aren't just talking theoretical fluff here, let's look at the actual deterministic math baked into every optimization. 50% of the weight goes to word overlap. 30% goes to constraint phrase survival, meaning did your core rules actually survive the process? And the final 20% goes to task type match. Basically, does a question actually remain a question?
So, when you crack open your system's metadata and see a shiny score like 0.98 attached to an optimization result, you have hard mathematical proof that your agentic instruction is still highly reliable. It means the optimizer successfully preserved all structure and intent. Now, if that score drops, that's an immediate, blaring signal to review the output before your downstream systems consume it and break.
Next up, guardrails, preserving intent and logic, which covers pillars 2 and 3. We're moving into our active defense mechanisms here to see how we build a protective shell around our workflows.
Pillar 2 is task type anchoring. Think about what happens without this. You might have a prompt asking, how do I configure rate limiting? But during optimization, it morphs into a statement. Configure rate limiting as follows. That is called question intent drift, and it will completely shatter your agentic routing and downstream parsers. Pillar 2 stops this cold by appending a static, strict instruction to the LLM. It's a hard guarantee that a question doesn't mysteriously transform into a command. Then we have Pillar 3, causal language preservation. We're talking about words like unless, only if, provided that. These are literally the load-bearing pillars of conditional logic, and LLMs absolutely love to paraphrase them incorrectly. Only if suddenly becomes when. Requires that softens into should. In software architecture, those paraphrases carry completely different truth conditions, and that's incredibly dangerous.
So, how do we fix it? Pillar 3 uses a really clever dehydration and rehydration process. First, we detect these causal connectors. Then, we wrap them up in special preserved tokens before the LLM even gets to see them. This dehydrated prompt then passes through the optimizer. Finally, we rehydrate those original phrases with 100% fidelity.
This completely secures your conditional logic, making sure that your critical security constraints and rules survive the optimization engine totally untouched.
All right, on to upstream validation, catching contradictions. This is pillar 4, our pre-flight check.
You know when you feed prompts to an LLM so it can instruct another LLM? Structural contradictions are just disastrous. Pillar 4 extends our conflict detector to catch these things upstream. Look at this table. If an instruction says always include examples, but 3 paragraphs later says never include examples, that is a critical severity conflict. Catching these LLM interaction conflicts upstream prevents super unpredictable downstream agent behavior. It basically saves you from tearing your hair out trying to debug fundamentally flawed instructions before the optimization cycle even begins.
And finally, we arrive at telemetry for long-term reliability, pillar 5, because a robust architecture has to monitor its own long-term health, not just celebrate point-in-time successes.
Pillar 5 is all about margin drift tracking. Now, you might be wondering, what exactly is margin drift? Well, a system can consistently pass your basic binary quality thresholds while its safety margins are actually quietly eroding in the background. Margin drift monitors how close our context classifiers are to a failure boundary. When the gap between your top confidence score and your runner-up score starts shrinking, your system is under pressure. Margin drift makes that invisible degradation visible.
Let's see how this actually plays out in production. Week 1, your median optimization fidelity score is 0.85. Fantastic. But by week 2, it degrades to 0.78. Technically, it's still passing your baseline alerts, but because we're tracking the median margin over time against a calibrated baseline, Pillar 5 sees that the gap is narrowing and triggers an elevated warn alert right in week 3. You get this critical early warning that optimization quality is slipping way before it breaks parsing and definitely before your users start filing complaints.
The blueprint complete, mapping defenses to failure modes. Let's bring this entire matrix together and see how these 5 pillars lock into place to secure your workflows. This right here is your complete architectural map, directly linking the specific failure modes we've identified in recent system audits to the deterministic guardrails we've just deployed. We lacked a measure of faithfulness? Boom, we built the Pillar 1 fidelity score. Task types drifted? We anchored them with Pillar 2. Causal logic kept vanishing? We preserved it with Pillar 3 dehydration. Contradictions broke our agents. We flag them upstream now with Pillar 4. And invisible degradation? That's entirely caught by Pillar 5 telemetry. As we hurtle toward fully autonomous agentic workflows at scale, it really begs a massive question. If your automated pipelines optimize themselves, who monitors the optimizer? Are you trusting your infrastructure's reliability to hope or to guaranteed structural correctness? Moving from simple token reduction to a multi-pillar correctness architecture ensures your pipelines are actually ready for deployment, not just slick demos. Thank you so much for joining me on this explainer, and I highly encourage you to go look at your own pipelines and ask yourself, just how structurally sound are your optimizations?